Hey everybody, it's March 28th, 2022, and this is Introduction to Statistics, Math 21 at College of the Sequoias. We are on section 9.3, chapter 9 was on confidence intervals. Is that what we were doing, confidence intervals? What was chapter 9? Yeah, chapter 9 was confidence intervals, right? Yeah, for proportions and means. So I'm gonna, this isn't part of your homework set, but I think it's a pretty good lesson area. And I actually added it to the teaching, and it's really 9.3. I'm switching to a handwriting thing where I can write like this. It's a little easier than the tablet. And 9.3 is more of a, which one should I use? When doing a confidence interval. And this will translate to hypothesis testing as well, which we will touch on today. Let me know if I need to write bigger or anything like that. So we have data. Data comes in two forms. We've got, and you've seen them, we talked about them before, qualitative and quantitative. Right off the side of the paper. Quantitative and qualitative. So let's look at what each category gives us. If we have qualitative outcomes, this is like hair color and name and you know, location, stuff like that. And in particular, when there's only two outcomes. Such as, you know, like a yes, no situation, success or fail. Even something like a Republican or Democrat. We could have numbers in there under 21 or less than 21 or greater than 21. That could be used to represent age. But even though they're numbers, I can turn this into a quality by putting them into two groups like that. When we have stuff like that, what we're really looking at is any situation where a portion of the population has the trait or characteristic and the rest do not. When we get to that scenario, we are looking at proportions. And recall we represent that with p hat. And we had some criteria to use it. N times p times 1 minus p has to be greater than or equal to 10. And n has to be less than or equal to 5% of the population. Those are our criteria. And if we have those criteria, this means it's normally distributed. Or approximately normally distributed. I don't know if green's coming in very well. What happens if I turn off that light? I don't know that that helps. It's normally distributed. I'll stop using green. I'll put that off to the side. And in those scenarios, what do we have? We got mu of p. P hat is p. And sigma of p hat is p times 1 minus p divided by n. Those are our mean and standard deviation. The other part of the other outcome is quantitative. I'm going to use green again just for a second. It's just the glare in general, isn't it? Quantitative. And here they need to give us a table or column of data. Or summarized data that includes the sample mean and the standard deviation. When we have that, we're looking at means, of course. This is the mean section. And the criteria for normal distribution here, we want normally distributed. And so if n is greater than or equal to 30, this is like the auto win category. We automatically have it. No more work is needed. If n is greater or less than 30, we got a couple things we need to do. Do a box plot to check for outliers. We don't want any outliers. And we do a QQ plot for the correlation statistic. Which is R. And then we compare R to the critical value. And we want R to be greater than the critical value. And that the critical value came on a table. You just have to look up, it's based on N, the sample size. I'll turn it off and see if that does help. Any questions? All right, let's look at some sample problems. Like it doesn't specify which one's which. In 9.1, you knew they were proportions. 9.2, you knew they were means. So I just grabbed 3 problems from 9.3, which don't tell you. So we'll take a look at that. And I made a little section, and it specifically says part of lecture demonstration. You don't have to do. If anybody asks me if that's part of their grade, I'm just going to give them an automatic F for not not having basic comprehension skills. I don't know if I can do that. Probably not. Does anyone need that page up longer? Again, if it's not clear, or if I need to write bigger, let me know. Okay. So let's take a look at this problem. Oh, that's kind of big text. Let's see what it says. A baseball's pitcher most popular pitch is a four-seam fastball. The data below represents the pitch speed in miles per hour for a random sample of 15 of his four-seam fastballs. They give us a table of critical values for the correlation coefficient. This is already screaming that mean thing. And now they're asking some questions for some comprehension stuff. So maybe I'll make that full size. Is pitch speed a quantitative or qualitative variable? Well, it's got a number, and it's not really like, we can't throw them into categories. Well, we could, but generally those are numbers, and we could find an average speed. So this is definitely going to be a quantitative variable. This is important to know because confidence intervals for a blank, so mean or proportion, are constructed on quantitative data. We know that's mean. We just got done talking about that. While confidence intervals for a proportion, the other group, is constructed on qualitative data with two possible outcomes. We want a yes or a no. So we just got done talking about that. So we're going to draw, they're prompting us. So let's get this over in StatCrunch. That does not get any smaller. So we'll come over here. Oh, maybe I should copy to clipboard. Since I've already got it open, I'll come over here and paste it. You can also do a right click, I think, in V, or edit paste. I did Control V. It says do a normal probability plot. That's the QQ plot. So I'm going to do the QQ graph, QQ plot. I'm going to add the correlation statistic because I'm going to probably want to know it. And the normal quantiles, that's that expected z-score along the y-axis. So I do that there, and it looks like they're roughly rising. It looks like it's almost a straight line, and it's going from -1.5 to 1.5. Which one of these has that? D looks like the closest one to, oh wait. The speeds go from 86 to 93. So that would be 80 to 90 to 100. This would be 80 to 90 to 100. I think we want D. We want the one that's closer to 85. Use the correlation coefficient. That's good. I got it. Of the normal probability plot, is it reasonable to conclude the population is normally distributed? Okay, since the absolute value of the correlation coefficient between the expected z-scores and the observed data, which I have right here, I'll just type it in, is blank. So we need to make a comparison to what? The critical value. So let's go grab the critical value from the table they give us. They said there was 15 samples. So we're looking for n equals 15 is 0.939. And 9.992 is bigger than 939. That would be exceeds. And that's what we wanted. We wanted our correlation coefficient to be bigger than the critical value. It's reasonable to conclude it is. That's what I was actually asking, is or is not. It is reasonable to conclude because it was bigger. Everything came in 3 decimal places, which was good. So now it says do a box plot. All right, we're done with that one. We'll do a box plot. And I'll draw boxes horizontally, and we definitely want to have outliers identified. And I don't see any outliers. So we want to find the one that looks kind of like evenly shaped. Only B and C look evenly shaped, but B has an outlier. So I'm going to go with C. And that's what we wanted. We wanted correlation coefficient to be greater than the critical value, and we wanted no outliers on a box plot. So the requirements are satisfied. So an interval can be constructed because the data are approximately normally normal and there are no outliers. It's funny, I think I say data is a lot, but data is technically the plural form of the word. Datum is singular. It just seems like everyone uses data as a singular as well. Construct and interpret a 95% confidence interval. All right, that's easy to do in here. We're going to do stats, proportion stats, one sample, and we have the data. So we're going to say with data. Wait, this isn't proportion. What am I doing? What is this madness? This is a mean. Stats, t-stats, one sample with data. There we go. And it wants a 95% confidence interval. So we have the lower limit and upper limit right there. We just got to pick the right sentence. One can be, we want to, it should say confidence in there. One can be 95% confident, sounds good. This says 95% of the pitchers forcing fastballs. That's not what we want. That's not probably even true at all. And confidence intervals are not about probability, they're about confidence levels. So we definitely want A. And round to 2 decimal places. So I've got 88.27 and 90.82. Do you believe that a 95% confidence interval for the mean pitch speed of four-seam fastballs for all pitchers in a league would be narrower or wider? Well, this is just one pitcher. If we add more pitchers, some of them are gonna, have greater variability. They're not gonna be as tight as these numbers right here. Some will be tighter, some will be less tight. So the interval, so there should be more variability, which means we should have a wider confidence interval. Is that true? I think that's true. That sounds about right. All right, it says next question. Before I go to the next question, I wanted to show you something. See if I got this down pat. I'm going to go into the normal calculator because we said this is a normal distribution, right? Or it can be approximately normal. So I'm going to go in here and put in the sample mean. And I'm pretty sure standard error is standard deviation. So I'm going to change that to put that right there. And I'm going to click on between. And rather than putting numbers right here, we were looking at a 95% confidence interval. So I'm going to say I want 95% of the area. And apparently that is not the standard deviation. Standard deviation is close to that. We could compute it. We need the sample mean divided by the square root of n. What is that? Sample mean was 89.546667. That's going to be off. That's not right. I'll show you this on proportion. I'll come back to this on another day. Proportions coming up a little bit. I want to show you a connection between the confidence interval and the normal calculator. I don't want to do a similar question. I want to go to the next question. Next question is a simple random sample of size n equals 40 is drawn from a population. The sample mean is found to be X bar is 121.4, and the sample standard deviation is found to be S equals 12.3. Construct a 99% confidence interval for the mean. So n equals 40. This is a mean. They're even telling us. So we needed to check, was n greater than or equal to 30, and it is. So we're already normally distributed. We can go straight to our calculator. This time we have a summary, so we're going to use that. And the sample mean they gave us is 121.4. The sample standard deviation is 12.3. And sample size was n equals 40. And they wanted a 99% confidence interval. So we'll select 99%. Oops. And click compute. And put that in. The lower bound to 2 decimal places is 116.13. And we got 126.67. By round. And that's it. So that was another mean one. And here it says on problem number 3, in a survey of 1,020 adults, the polling agency asked, when you retire, do you think you will have enough money to live comfortably or not? Of the 1,020 surveyed, 534 stated that they were worried about having enough money. Construct a 95% confidence interval. So we'll do that. Let's see, do we meet the criteria? Let's take a look at that real quick. So this is a proportion one. P hat. And so I've got 534 is my successes. And we've got 1,020 for our sample size. So our p hat is x over n is 534 over 1,020. Okay. So we need to do the n times p times 1 minus p. Times p hat, which I'm not going to write down because it's a lot of decimal places, times 1 minus p hat. And I have that stored in my calculator, so I can just do that. I can do 1,020 times my answer times parentheses 1 minus answer. And I'm getting 51.14. I don't need all the decimal places because all we were trying to check to see is this greater than 10? Yes, it is. And then we needed to check to see if n is less than or equal to 5% of the population. I don't know the population, but I'm assuming if we're looking at a country or something like that, or even a city, 1,020 is less than 5% of the population. It's a lot less. So we meet the criteria for it. So we're going to put that in the proportion calculator. We do not have the data, so we're going to say with summary. There were 534 successes out of 1,020 observations. And we want a 95% confidence interval. And so we have our interval right here, the lower limit and the upper limit. And we want to use the one that doesn't say probability, that doesn't say that 95% is definitely in there. We want to go with one that says confidence. And they said round to 3 decimal places. Use ascending order means do the lower limit first. So I've got 0.493, it looks like. And for my upper limit, I've got 0.554. Okay, so I'm going to show you on this one. I wanted to show it because it's easier to calculate here. For probability distributions, p hat is our mean. And then standard deviation is p times 1 minus p divided by n, and we take the square root. So my mean is just that 0.05294. I'll do 5 decimal places. And sigma is square root of 0.05294 times 1 minus that. Divided by n, which is 1,020. What happens if I turn that light off and turn that one on? They're both just too bright. And that's almost too dark. Is that too dark? Or is that more visible? Anybody? It's more visible. Okay, I'll leave it like this. Okay, so I've got, I'll take the square root and I'm going to do, well, I'll do the square root at the end. I'm going to do the numbers. I'll put 0.0. I'll re-get the number by doing 534 divided by 120 or 1020. And now I'm going to do answer times parentheses 1 minus answer. That's my top portion right here. And then I'm going to say divided by 1020. And that gives me part of the answer. Then I need to take the square root. I need to light on for a second to read what it says. 0.015638262. All right. Let's take a look at the normal calculator here. I'm going to put those values in. 0.05294. And we just calculated 0.01563. 8. We'll do that. That's good. And I'm going to click between. I'm going to say 0.95 over here. Did I do something wrong? I totally did something wrong. There's no way 534 divided by 1020 is that value. I'm off by a decimal place. Which means that's off by a decimal place, which means this is off by a decimal place, and I need to recompute that. I knew that sounded funny when I said 5% earlier. That didn't sound quite right. Oh, that one was right. This one was not. And something's off in my rounding. How is, what in the hell? I'm even getting the wrong number here. Good God, Jones. 2, 3, 5, 3. There we go. I knew it was supposed to match up. So I knew I was doing something wrong. Notice, this is what that's what I want to do. When you finally have the correct mean, x over n, and you calculate sigma correctly, and I had the right sigma there, and you put them in the normal calculator, The 95% confidence interval, the lower limit right here, notice the 4 decimal places, that's 4929. And look what I have right here, 4929. And when I do the upper limit to 4 decimal places, 0.55417 goes up to 42. I have that here. So confidence intervals are really generated from using the normal calculator, from using a normal distribution and determining what area has been captured. I'm gonna say captured, it's the stuff in red. If I change this to a 99% interval, it covers more. And I can do this right up here by editing this one and showing the same thing. .4832, 0.5638. So they're directly related. And that's kind of handy to recognize, handy to know. Okay, let's take a look at hypothesis testing. We're going to start chapter 10. So, where is my other pen? That's scary. What did I do with it? I had 3 pins out, one's completely vanished. Oh well. Does that help? I got an idea. Let's see, how do I do this here? That didn't help at all. That does. All right. I'm going to write bigger because I need the light on to read what I want to write to say. But I will write bigger to compensate for that. Turn that off. Don't need the homework open. I'll leave StatCrunch in case I want to use it. Let's talk about hypothesis testing. So 10.1, we're just introducing it. 10.2 we'll do on 10.2 and 10.3 we'll do on Wednesday. That's where we start using them in particular examples. So you and I, we play a game. Let's play a game. And I'm not actually going to do it because I want to show a certain outcome. And I'm going to say, I'm going to flip a quarter. Heads You pay me $1. Tails, I pay you $2. Sounds like a pretty fun game, right? And we play this game and we flip it 6 times. Oh, I might have to turn this off. See if that comes through better. Those are all heads. I need to change the lighting in here. That's what I need to do. So we get 6 heads. Okay. We get 6 heads. And you owe me $6. And you start asking me. I found my pen. I'm stepping on it now. You start asking me, did Jones cheat? Heads. Heads. Did Jones use a double-headed coin? Is that how he won? So let's look into that. Did Jones use a double-headed coin? They exist. I just showed you one. Well, we went into the game. We made a specific assumption at the beginning. We assumed that the probability of the flip being a head was the same as the probability of the flip being a tail. Both of those would be 1/2 or 0.5, right? So what's the probability of 6 heads? I don't need that right now, so I can do that for a second. Well, that's the probability that the first one is a head. I'll say F1 is a head, flip 1 is a head. And F2 is a head. And F3 is a head. And we're going to go down the list and we get down to F6 is a head. That's not good with the red. I'll stop with the red. So when we have the and turns into multiplying. So this is the same thing as the first one being a head times the second one being a head times, we go down the list, the 6th one being a head. And each of these is 1/2. And I've got 6 of them. This is 1/2 to the 6th power. It's 1/64. And that is approximately 0.015625. Which means in 1,000 flips, You know what? Let's make it better. Let's go 10,000 flips. If I multiply this by 10,000, I get 156. 156 times out of 10,000 is the 10,000 sets of these. Can I expect 6 heads? And it might be more, it might be less, because you know how probability works. This isn't a fixed number, but it's expected. That's not very often, is it? Hell, even if we had just done it 5 times, probability of 5 heads, well, all this math stays the same. That's 1/1/2 to the 5th power. And this is 0.03125, which is approximately 3.1%. Even 5 heads, what's our unusual cutoff? Anybody? Is this unusual? I see some answers. I see 5%. It is. Yes, this is unusual. So where do we take that from here? I'll leave that up a little bit longer so you can finish writing it. In fact, let's take a 3-minute break. I'm going to use the restroom real quick. I twisted my knee this weekend and I've been walking like a duck ever since. Are you guys there? I didn't actually time that. Gabe's here. So Pablo, you here? All right. I'll assume that was enough time to write that. So we saw that this was an unusual event. So there's 2 outcomes here. 2 possible explanations of what went on. Scenario 1 is everything was legit. You are just unlucky. And scenario 2. Game was rigged. And Hefe cheated you, suckers. And for a game to be rigged, it either needs to be like a weighted coin, where like one side is much heavier than the other, so it always lands down, the other side lands up. Or you could have like a two-headed or two-tailed coin. Those exist. I just showed you one. I wish this one didn't start having little oxidization on it or whatever that brown is. I gotta have to see what I can do to get that off, because I like that coin. It's pretty cool. So guess what? This is a hypothesis test. We made an assumption about reality. We had initially assumed probability should have been equal. Half and half. But after 6 flips and getting something that is very unlikely to happen, we made a new assumption, new idea. He cheated. Okay. So in a hypothesis test, when the outcome is unusual, I forgot that red's not showing up very well here. Different color. When the outcome is unusual, we go with the new idea. And reject the old one. So what happened here? The outcome was unusual. So if I were you, so I, being you, would think Hefe cheated. That's how hypothesis testing works. That's a stake coin. You can see the tails on the back. In this case, you were not cheated. Hypothesis testing does not always give the correct answer. It doesn't always give the truth. Okay. Give you a second. Let's go with something darker where that doesn't stand out so bright. There we go. I didn't know. So it doesn't always reveal the truth. So let's talk about this a little bit more. Because guess what? In reality, when we are doing statistics, in real life, when we do this hypothesis testing, there's no one there to flip the coin over. You are never, ever, ever 100% certain that you're right. Unless you have access to the entire population. Unless you ask or do whatever for the entire population. Okay. But we can have a really good idea that under 3%, that under half of 3%, 1.5%, that's a pretty good indicator that that I had a rigged coin, that I used a rigged coin. So you have to go with what the evidence shows you to a specific level of confidence. So that's how hypothesis testing works. In general, we make an assumption about reality. And it's usually in contrast or comparison to something that came before, but not always. When we don't have something to compare it to before, we just pick a baseline. We pick what we think is the case. And we'll see an example of that on Wednesday. So we make an assumption about reality. In this case, the coin was unfair. Then we gather data to support or refute that claim. What we did here is flip the coin 6 times. Now notice I didn't start with the assumption that the coin was rigged. You wouldn't have played the game if you thought I was using a rigged coin, but you eventually came to this conclusion. And so we retroactively are using data that we just collected. It's similar in nature. This happens often when you're doing statistics in real life. You may have an idea of what you think it is, but after you've gathered a bunch of information, asked a bunch of people, you may change your initial assumption and create basically an alternate hypothesis. And that's what we did here. We assumed it was fair, and then after some data collection, we assumed that it was unfair. Once we have this data, once we've gathered it, we're going to use probability and analysis to make a decision about supporting or not supporting that claim. Okay. If you need this up longer, say something now. I might have to just put less bright bulbs in there. Okay, I don't see anyone saying anything, so I'll assume you're good. So in stats, a hypothesis test which I'm probably, if you see me write hype tests like that, I'm saving the time of writing hypothesis because it's a long word, right? In stats, a hypothesis test is a statement about a characteristic of the population. Or actually one or more populations. If we're breaking the population up into groups, sometimes we'll have one or more. Now, when we're talking about the entire population, that characteristic is called a parameter. When it's in terms of the sample, we call the results a statistic. So parameter is when it's the overall group. The kind of things we look for in here, though, we've got parameters are, let's make a list. Parameters versus statistics. And maybe I'll call this category.
We can't see what you're writing down on the paper, Mr. Jones.
You can't.
I think it froze.
No. Yeah, it froze or something.
Okay. Let me try this.
It just shows your hands.
You're
on
right. It did freeze. I see it froze. Your screen sharing is paused. Resume share. I hit something on the keyboard. It was Zoom. All right, I'll pause. So I didn't really show a whole lot yet, and I'll let you guys write that down. Thank you for saying so. I get busy writing and I don't always see chat. we're going to look at 4 categories. We're not going to do a lot with a couple of them, but these are the 4 most common categories. Proportion and mean are the 2 we do the most with. We could do standard deviation and we could do variance. So when we're talking about parameters, a proportion is P, while the statistic is P hat. The mean is mu, whereas statistic is X bar. Standard deviation, we use sigma with that tail. And for statistics or a sample, we use S. And variance is actually the square of standard deviation. So sigma squared or S squared. I don't know that I've ever frozen Zoom like that before. I wonder how I did it. If you need that up longer, let me know. A lot of this is old information, just reminding you of the different letters they use. We talked about that at the beginning of the semester, to be honest, but that's okay. Always good to refresh before we start hitting everything along. So I'm going to give you guys some scenarios and we'll discuss what the parameter is and what claims are being made. So example 1 or example 8, the milk fat percentage in California dairy milk. Get my calculator out of the way. In the year 2012, 10 years ago, was 3.72%. I pulled this from actual data. All these things that I'm covering today were pulled from actual data. I got this from the California dairy something or other. Researchers believe that a change in diet for the cows, of course, has led to a change in the percentage. My question for you is, what parameter is this being discussed here? Any ideas? I'll bring up what we just wrote. It's a little trippy, but percentage is often proportion. Is that what milk fat percent means in this circumstance, though? When they say like 2% milk, what are they saying? Because 2% is low fat milk. They're saying that the percentage or proportion of milk that's fat. So this happens to be a proportion parameter. The proportion was, if I write it as not as a percentage, I could say the proportion of milk fat was 0.0372. And so the old claim here was that P was 0.0372. That's the 2012 data. And the new claim by the researchers is that it's not 3.72% anymore. It's changed. They did not indicate whether the change has been an increase or a decrease. So when they don't indicate decrease or increase, we just say not equal to. Okay, here's another fun one about crops. Every inch increase in standard deviation of plant to plant spacing, like how far apart the plants are. In corn, we're talking about corn in particular, reduces the corn grain yield by 2.2 bushels per acre. Ideally, you don't want to have, you want the corn to be evenly spaced apart and not have it change. That was a true thing at a certain point. And then I don't think this was at the World Ag Expo, but I'm adding it in to make it local. As at the World Ag Expo, a machine creator claimed that their new product reduced the deviation from the previous amount of 4.5 inches. Well, this one's kind of easy to figure out what the parameter is because I actually mentioned it several times. The parameter here is standard deviation, which is the sigma symbol. And so we'll look at the old claim versus the new claim. The old claim has to be the previous amount. That sigma was 4.5 inches. And now the creator in their new product is saying they've reduced that, which means that it's gone down. It's less than 4.5 inches. Okay. And I'll do one more. If you need that up longer, go ahead and say something. All right. Let's see. Stats, final exam scores. Average 73%. We believe using computerized stats, us teachers, like StatCrunch, has increased the average score. I should say stats. There you go. What parameter are we talking about here? Well, the percentage makes it look kind of like a proportion. I see chat. That's right, Gabe. It is a mean. Even though it looks like a proportion, it says average. And the average is a dead giveaway that this is a mean. So we'll look at the old claim versus the new claim. The old claim was that the average was 73%. And the new claim, it didn't say what the value is. They just said that it's higher. So that's kind of like what we're doing in hypothesis testing. In hypothesis testing, we have two competing ideas. That was a blending of two words. In hype testing, there we go. In fact, hypothesis testing in itself is a procedure that uses probability and sample evidence to choose between two conflicting or competing ideas or claims. So we label them. We call them H0, and depending on the book, HA or H1. I'm going to use HA, but if you see H1, they're talking about the same thing. H0 is called the null hypothesis. And HA is called the alternate hypothesis. And that's not really an O, it's an H0. So they call the null hypothesis, it's pronounced H naught. It sounds like that. We say H naught. But not, that's not really the right spelling of it. It's more like H naught, which means it's not there, or it's effectively H0. Okay, but you'll hear H naught. I like to call it what it looks like. I like to call it the ho and the ha. Okay. What we want, what should be the case every time, the null hypothesis is a statement of equality. And that means we will see an equal sign in it. This is the statement that is assumed to be true. Give you a little bit longer with that one. That's the null hypothesis. The alternate hypothesis is an inequality, which means it can be less than, it could be greater than, or it could be not equal to. And this is the statement that we are gathering evidence to support. Or not support, depending on what the data gives us. So to put that all in like one idea, we assume H naught is true. And gather evidence to support HA. So we've got two outcomes. We can either support it or not support it, right? So how does the two outcomes, what are the two outcomes and how do we go about them? So one outcome is that the evidence shows that the null is true. I don't want to say it that way. Let me rephrase that. That's a poor way to say it. We never know that it's true. And let me start with the other one. Let me put it like this. If the null is true, then how do I want this? Then the results obtained are unusual. This is what we did with our coin flip. The null statement was that the probabilities were equal. In this case, in this outcome, we reject the null hypothesis and we support the alternate hypothesis. If the results obtained are unusual, the null we're going to assume isn't actually true. And we're going to assume that the alternate hypothesis is true. Again, we may be wrong. Like if you assumed I had used a cheater coin, you would have been wrong. The other outcome is if the results are not unusual, switch back to black. Then we do not reject H naught. And we do not support HA. You guys ready for a little bit more? All right, I'm sure you've all heard the phrase innocent until proven guilty. Right? That's what our system of law is all about. You're innocent until proven guilty. What are the two verdicts you hear in a law case, though? The two verdicts are guilty, or what's the other one?
Innocent
You never hear innocent in a court of law.
or not guilty.
Not guilty. It's not innocent. So like the statement is actually not good. It should be more like not guilty until proven guilty. Why do we not say innocent? Well, we never say innocent because we may be wrong. Because they may not, in fact, be innocent. There just isn't enough evidence to support a guilty statement. And that's why we have reject H naught, support HA. HA is subscript. Do not reject H naught. Do not support HA. And I get really, really dead tired of writing do not reject and do not support. God darn it. Stop using the red pen, Jones. Stop using it. It doesn't work for you. You'll see me write DNR H naught, DNS HA. These two things mean the same thing. So these are the two things we do every time, but our final statement should always be about HA. It's the one we're gathering evidence to support or not support. So I'll show you like a general statement of how we write it, and then we'll start looking at specific examples. Does anyone need that longer? Okay. So a general conclusion. There is sufficient, and I'm going to put / insufficient, because this is really the only thing that really needs to change for the main body of it. There is sufficient, insufficient evidence to support the claim that, and then you basically paraphrase the alternate hypothesis. If it's done, if the sentence is worded right, you can actually just copy and paste. It's almost like what a court of law does. They don't use that wording. They just go with guilty or not guilty. But if I were to look at the court of law example, And I wanted to label H naught and HA. H naught is the one we assume to be true. So for a court of law, that would be not guilty. And the alternate hypothesis would be guilty. That's to give you the idea how this relates to a court of law. Well, we're going to go back to some of the problems we actually have. Let's look at the coin flips one we did. What we had was we assumed the probability of the flip equaling a head was 0.5 or 1/2. The alternate hypothesis, and it was not 1/2. In fact, I flipped a head every time. So not 1/2 is probably a bad thing to use. We should probably say we thought it to be greater than 1/2. The one that has a statement of equality, the equal sign is my H naught. My coin flip, or the alternate hypothesis, the inequality, the greater than, that's my HA. So in terms of that conclusion I had above, we showed that it was unusual for the coin flips. The results were unusual. So we reject H naught and support HA. We reject the fact that it was a fair coin and support the fact that the coin was unfair. So if I were to make a conclusion statement about this, there is sufficient evidence to support the claim because I'm supporting HA. That Professor Jones, Professor Hepe is a cheating bastard. That's kind of how it would be. Or maybe not a cheating bastard, but used an unfair coin would probably be something you would see. We'll go over our other examples real quick. We won't do outcomes for them yet because we didn't have results for them. Can't say unusual or unusual. But I want to give you guys some more practice picking H naught and HA. So for the milk fat, I had P equals 0.0372 and P did not equal 0.0372. For the corn yield one, I had standard deviation was less than 4.5 inches. That was the new machine. And then we had standard deviation was 4.5 inches. And then we had our average test score problem. And we had the average was 73%. And the average was greater than 73%. For the milk fat one, which one should I call H naught? Should I call the top one H naught or the bottom one H naught?
The top one, right?
The top one, that's correct. Why do you say that though?
Because that's the standard, the what we were given beforehand.
Yes. It also has that equal sign in it, which means the other one's got to be HA, right?
Hmm.
What about corn yield? What's the top one here?
It's equal. The equal is 4.5 inches.
Yeah, this one should be the, I think this is what you're saying. That's the H naught.
Yeah.
That's the HA. And the average test score, what's the top one?
The top one's H naught.
Good. So we're looking for that equal sign, and that's H naught. A well-designed experiment, this is the scenario. Has that set up. The custom, I didn't do it on this, on the corn yield, but the custom is list H naught first, then HA. I just changed it up on corn yield that way because I wanted you to not just automatically go in order every time. It should be the one with the equal sign. All right, we'll call that a wrap for today. I will finish up today. I only had a little bit more for 10.1. And 10.2 and 10.3 we will do on Wednesday. And I think we might be done early on Wednesday. I don't think they take a long, well, I don't know. We'll see. We may not be done early, but we'll call that a wrap for today because we're out of time, really.
Okay. Thank you, Mr. Jones.
Thank you. I'm glad you guys can make it.